Hello again, welcome back. So today we're looking into capacitors and capacitance. So first and foremost, I would like to introduce to us what a capacitor is before we move on to capacitance and necessary calculations involved. So let's see what a capacitor is. A capacitor is a device that has the ability to store electric charge. That is a component of electric circuit that can store electric charge after it has been what? Recharged. That is, it is essential for us to reuse the electric what? Charge that has been stored in every of our electric appliances. For instance, our electric touch, and we have even in our cell phone we have a component that stores electric charges. For instance, if you have to charge your phone and you observe probably the phone does not increase from one percentage to another percentage. So what is faulty there? We say it is a component of it which is called a capacitor. Even our lamp, our touch lamp, our lamp, it can also be the cause of it. So once a capacitor is faulty in our electric appliances, then you can see the capacitor happens to be faulty. So a capacitor is that device that has the ability to store electric charges. So that's what a capacitor is. So a capacitor stores electric charges. So that's mainly the primary use of a capacitor. Now, again, what other uses of capacitor do we have? What other function can a capacitor have? One of it is to what it is used mainly as it's known is used to store storage of electrical or electric charges. Again, a capacitor is used to separate an AC circuit from a DC circuit. That is, an AC circuit is an alternating current circuit, and this circuit is a direct current circuit. That's what um, an AC and a DC circuit is. Again, it's used to so this this is what the capacitor is used for, to separate an AC circuit from a DC circuit, also to store what? Electric charge. Also, you can even use it to control current currents using controlling currents in AC circuit. Using controlling currents in what? In a DC circuit, sorry. In a DC circuit, that's what a majorly these are the functions or the uses of a capacitor. Now moving on to what we call the capacitance this time around. Let's move on to capacitance. So what is a capacitance and what is a what? Capacitor. You are able to tell what a capacitor is. That is, a capacitor is a device that stores electric charges with this function in the storage of electric charges, in the separation of an AC circuit from a DC circuit, and in the control of current in a DC circuit. Now, a capacitance. Now, what is capacitance? A capacitance is a property which enables this device to store electric charges. So the measurement of the storage of electric charges in a circuit is what we call a capacitance. And a capacitance can be expressed or measured. So the measurement of each of these is what we call the unit is called farad. So a capacitor is measured in farad. It can be also be expressed mathematically, or it can also be defined mathematically by saying electric charges Q is direct proportional to the what? Potential difference or voltage. So Q can now be equals to CV, where this C is what we call the capacitance of our interest. So it means C Making Q so the formula C can now be equals to Q electric charge over potential difference or voltage. So the unit for this capacitor is now expressed in farad, farad F, but commonly we use it as microfarad. So whenever you see in the capacitor, they say anything, they give you a value, and you are given something like 2 microfarad, it means this is a capacitance. So this is the amount of electric charges per unit voltage that will be stored in a capacitor, and that is the measurement of capacitance. Now, since on knowing this, where you can say capacitor stores electric charges, this is the device, and the measurement of the storage of the charges is what we call capacitance. So these capacitors can be arranged in different forms. So we have the forms of arrangement, that is the arrangement of capacitors. The arrangement of capacitors. One, we have the parallel arrangement, and we have the what? Series arrangement. So, on knowing we have arrangement of capacitors, we have the parallel arrangement, and we have the series arrangement. So these are the two major arrangements of the capacitors we have in our electric circuit. In our electric circuit, these are the arrangement. We have the parallel and we have the what? Series arrangement. Now we have to understand when capacitors are said to be arranged in parallel, when capacitors are said to be arranged in series. Is very essential and very necessary. How do we distinguish parallel arrangement of the capacitor from series arrangement of capacitors? Now let's go. Parallel arrangement of capacitors. Now, when we say capacitors are arranged in parallel, capacitors are said to be arranged in parallel when they have the same amount of potential difference to flow across them, but different electric charges. That's just how we can identify them. Now they are said to be arranged in parallel when they have same voltage, or you simply see potential difference, but different different charges, but different charges. So basically, this is how we identify a parallel arrangement of the capacitor from series arrangement of capacitors. Now let's see illustration of a parallel arrangement of capacitor. Let's say we have this. Let's say we have this, something like this. Let's say we have something like this. We have this. So you have this. This will be where we have the potential difference, and then each of the capacitors are here. The capacitor 1, the capacitor 2, and capacitor 3. Each of them with their respective charge 1, charge 2, and charge 3. Now, and charge 3. So from here, we can say they have the same voltage or potential difference flowing across them, but different charge. You can see that this capacitor 1 has its charge 1, Q1, capacitor 2 has its charge 2, and capacitor 3 has its charge 3. Now, don't make a mistake in taking a capacitance for cell. Capacitors, capacitance have equal length like this, but for a cell, has one to be longer than the other. So you have to be very careful with your symbols. This is cell and this is capacitor. Now on knowing this, you can now come and see. So for this particular electric circuit, we are able to establish that the capacitor have the parallel arrangement of capacitor have the same voltage but different electric charge, which implies that this if two voltage should flow across capacitor 1, the same voltage will also flow across capacitor 2, the same voltage will also flow across capacitor 3. That's what we are telling us now. So it's very essential for us to know the total electric charge that will flow. From here, we know that capacitance voltage and charge, they are related with this formula Q equals CV. So if Q equals CV, so you can now say you can have total charge that has to flow across them is equal to the charge that will flow across capacitor 1 Q1 plus the one that will flow across here Q2 plus one that will flow across the third one Q3 up to wherever you are going. Either if it is more than 3, just if it is 5 Q4 Q5. If it's 10 is Q4 Q5 Q6 up to Q10 in that order. Now we can now say that okay, we can say Q is CV from what we have, Q equals to CV. So since we are interested in the total charge here, you can now see this is C total times V. Since V is the same thing here, so the same V will be here, voltage equals C1 for Q1. So Q1 will now be C1 V. Since the same voltage will flow across them as known, plus C2 V plus C3 V up to CN V. I hope you are getting this. Now from there, we can look at this. We have V here, we have V here, common to them. So we can factorize this right hand side. You can say CTV equals. Now let's factorize what is common to them. What is common to them? We have the voltage to be common to them. So V. Now factorize. What are we left with? C1 plus C2 plus C3 up to Cn. Up to Cn, as you can see. So since if it has been known that V can eliminate this V out, then you can now see our total capacitance C total equals C1 plus C2 plus C3 up to Cn. So this is how we can calculate for total capacitance in parallel. When the capacitors are arranged in parallel, we can just say your total capacitance is just the C1, C2, C3, add whatever. It means it's the algebraic summation of each of the capacitors we have in the what? In the arrangement. So for instance, let's take an example. Let's take an example. Let's say we have this. Let's take an example. Let's say we have this. Let's say we have something of this nature. Let's say we have something of this nature. Let's say this we have 2 microfarad, 3 microfarad. I have another one. Let's say we have another one of 5 microfarad. And we have like 12 volts here. So let's see the amount of total capacitance that will be present in this circuit. So as known, C total equals C1 plus C2 plus C3. Only 3 here. So you can now see your C total. What was C1? 2. Your C2, 3 plus C3, 5. So by the time we sum this, 2 plus 3, 5 plus 5 making 10 microfarad. So hence, this explains, this gives total capacitance in these capacitors in parallel. So I want to believe parallel arrangements happens to be clear. Now, parallel arrangement, as known, same voltage will flow across them. Basic difference between them. If you have the same voltage, a parallel arrangement but different electric charges. So as majorly we have it like this. Even sometimes you can have an illustration showing something like this. Don't be confused at all. Don't be confused. Don't be confused. If you have something like this, and have another one, and have another one like this, and have something like this, a terminal X here, and that terminal Y here. So you can tell you this is 4 microfarad, can say this is 6 microfarad, and can say this is around 5 microfarad. So by the time you do this, you can see it should just be, since they are parallel, you can see they are parallel, just like this, so they are parallel. So you can say the total capacitance C total can now become 4 plus 6 plus 5. So 4 plus 6 gives 10 plus 5 it gives 15. So it means something like this. is a parallel arrangement of capacitors. Now, after explaining arrangement of capacitors in parallel, which we said capacitors in parallel are said to have different charges for the same potential difference or the same voltage. Now we take series arrangement again. So series arrangement, when we say capacitors are said to be in series, is just opposite of parallel arrangement. So series arrangement, we have them to be arranged in series when they have the same electric charge but different potential difference or different voltage. So in series arrangement we have same charge, we have different voltage, or you can just say potential difference. Now that's just it. That is, they will share the same amount of charge that will flow across them, but different amount of what potential difference or voltage will flow across them. Now let's see an illustration how you can identify capacitors to be in parallel and to be in series. Now let's see this. Let's see this. Can see, can see. If this happens to let's see the potential difference of each of them here: V1, V2, V3, and this is C1, capacitor 1, capacitor 2, capacitor 3. So having the same amount of charge that is flowing across them, let's say we have the charge here flowing across them, because we can see on this point to this point, they are mostly ends to ends. They are mostly, so just like this, you can just say like this, like this, like this. So you can just give question like this. You can see it's actually similar. You can just construct it to be like this. As you can see, you can just construct it to be like this. Then you can see it's the same as this. Now, since we've known this, capacitors for series, they will have different potential difference, but they have the same amount of charge. So since we know that the amount of charge is the same thing, but different potential difference, so we need to know the overall potential difference that will flow across them. So sorry, so we can say total potential difference V total, because in parallel arrangement we look for total charge. So in this series arrangement we have to look for total potential difference, because that's the reason that is different between them. So V total potential difference of voltage equals to the first one, the V1 plus V2 plus V3 up to Vn, if up to more than 3, 4, 5 in that order. Now we can recall by saying Q equals to CV. So we are trying to look for the V. So make your V set of formula. So your V can then become Q over C when you divide both sides by C. So you can now say V equals to Q over C. If that should be the case, then your V total is equals to V. So your V total will now be Q over C total, since they have the same charge. So that becomes Q over C total equals Q over C1 plus Q over C2 plus Q over C3 up to, if you have more than 3, Q over Cn. So if that should be the case, now since we know that Q is common to both of them, I can just say this is 1 over C total times Q equals to, now let me factorize what we have common to them here. We have Q common to them. Then what we have left, 1 over C1 plus 1 over C2 plus 1 over C3 up to 1 over Cn. So from here, I can say this my Q, can eliminate this Q. I can say this my Q, can eliminate this Q. So I can say 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over C3 up to 1 over Cn, as you can see. So it's just different from parallel arrangement. Parallel arrangement is just sum everything together, but for series is the inverse of each of them. So you just 1 over C1 plus 1 over C2 plus 1 over C3 up to 1 over C. So we can now see that our 1 over C total equal 1 over C1 plus 1 over C2 plus 1 over C3 up to 1 over Cn. It gives total how to determine our total capacitance for series arrangement. Now, from there, let's see an instance. Let's have an example. An example. Let's say we have something like this. Let's say we have something like this. Or better still, let me just give a simple illustration. Simple illustration. A simple illustration from point X to point Y. So let's now say we have 2 microfarad, 4 microfarad, and we have 6 microfarad. So we have to determine the effective capacitance. So to determine the effective capacitance, it means you should look for the total capacitance. You have to calculate for the total capacitance, or they can ask you look for the total capacitance, calculate for the effective capacitance, or you should calculate for the net capacitance. Now, since we have known that, so we can say 1 over C total, the solution now. So 1 over 2 plus 1 over 4 plus 1 over 6, as you can see from the formula. So 1 over C total, and then the, now from here now we can see this is fraction. How do we resolve the fraction? We find the LCM. So what is the LCM of 2, 4 and 6? That is the smaller number, the smallest number, that 2 can go in the number without a remainder, 4 will go in the number without a remainder, 6 will also go in that number without a remainder. So the number is 12. So 2 in 12, 6 times 1, 6 plus 4 in 12, 3 times 1, 3, 6 in 12, 2 times 1, 2. So you can now see 1 over C total equals 6 plus 3, 9, 9 plus 2, 11, 11 over 12. So 11 over 12. So from here you can cross multiply from here. So C total times 11, that is 11 C total equals to 12 times 1, 12. So by the time you divide both sides by 11 here, 11 here, so your C total equals to, this is equals to 12 over 11. 12 over 11 microfarad. And that gives the total capacitance of these capacitors in series arrangement. Mind you, if you have to solve this question, you now stop at this stage, only 11 over 12. Trust me, you are wrong, because well, the only thing you got is just the 1 over, not the total capacitance itself. So you have to take the inverse of it. So whatever you have on this side, for instance, you have this your 1 over 6 total to be 2 over 6. So your 6 total will just be simply become 6 over 2 by taking the inverse of both sides. So and that will become what? 3. So trust me, if you have this in the option, you will definitely have this in the option microfarad. You also have this in the option. But what will have been the correct answer? This will have been the correct answer. So I want to believe at this stage we should be able to distinguish the difference or to identify when we have a total capacitance and when we have a series arrangement of the capacitor and parallel arrangement of. As we said earlier, a capacitor is a device that stores electric charges, and we have 2 forms of arrangement of capacitors. We have the series arrangement and we have the parallel arrangement. When they say we have parallel arrangement, we have parallel arrangement when they have the same voltage or potential difference flowing across them but different electric charges, which is just the summation of the total of the capacitance of each of the capacitors. Q total is equal to Q C1 equals to C2, I mean C total equals to C1 plus C2 plus C3, but if more than 3 plus the number. But if you have it in series, we have 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over 3 up to 1 over Cn. So in series, you said they have the same charge but different voltage. So at this stage, I think we should be able to solve any question that are regarding or as regards capacitors in series arrangement or parallel arrangement. So kindly follow this page, press the like button to follow more for more of this. Thank you once again.